Hello and welcome to the magical journey of science and sleep. Tonight, we will drift together through the soft folds of space, not the messy stuff in your room, but the endless curves and twists between galaxies, where time and space seem to dance to the rhythm of the universe. This is an experience where you can both relax and explore, a delicate combination of stillness and imagination. Before we dive into the wondrous maze of the cosmos, hit the subscribe button and turn on notifications so you don't miss a single moment of this journey. And if you enjoy this video, a gentle like will help this little peaceful corner of the internet continue to grow. Stay until the end of the video, because the most magical things in the universe sometimes appear only in the final moments. You can imagine that shape, something we consider familiar, is actually just a thin curtain covering deep mysteries. As children, we learn basic shapes: triangles, squares, circles. They appear in toys, in the alphabet, on streets, and even in textbooks. A child only needs to point at an object and say, "This is round, that is square," and that is enough. But that is only true within the narrow world of everyday experience. Step beyond that familiar realm into the infinite expanse of the universe, and we see that the concept of shape is no longer simple. Space, where stars, galaxies, and massive black holes reside, does not follow the rules we once knew. There are no edges to measure, no angles to determine. Space is not an object, but a soft fabric, stretching and bending according to the mass and energy it embraces. We can begin to understand the universe by turning back time, returning to the ancient years when our ancestors first gazed at the night sky. Before equations, before telescopes, humans paid attention to shape. They carved circles into stone, aligned monuments with the sun's path, and observed the cycles of the moon, not merely for beauty or curiosity, but for survival. Crops, tides, and the movement of celestial bodies were all related to cycles and patterns. And from this, geometry was born, not in classrooms, but on fields and riverbanks, where humans learned to measure, navigate, and survive. The Egyptians used geometry to mark land boundaries after the Nile floods. The Babylonians mapped stars into grids, and the ancient Greeks, especially Euclid, systematized all geometric knowledge into rules that continue to influence us thousands of years later. Euclid set out simple and clear axioms. A straight line is the shortest distance between 2 points. Two parallel lines never meet, and the sum of the angles of a triangle is always 180 degrees. Euclidean geometry dominated human imagination for over 2,000 years, describing everything from pyramids to planetary orbits. It created a sense of certainty, clarity, and satisfaction. But gradually, its limits became apparent. Do parallel lines truly never meet? Is space really completely flat? In the 19th century, pioneering mathematicians like Carl Friedrich Gauss, Nikolai Lobachevsky, and Janos Bolyai began challenging these limits. They imagined non-Euclidean geometries, where straight lines could intersect, where the sum of a triangle's angles could be greater or less than 180 degrees. These ideas were once considered extreme, but they opened the door to the concept that space itself could bend, stretch, and even twist in ways everyday experience cannot intuitively perceive. Then Einstein appeared, turning these imaginations into physical reality. With general relativity, he showed that it is not gravity pulling planets together, but mass and energy bending spacetime around them. Planets, stars, and even light follow these curves, and we can observe these effects, such as gravitational lensing, where light from distant galaxies bends as it passes through warped regions of space. There is no doubt the shape of space is a physical reality, not merely an abstract concept. What is fascinating is that this shape is not something we can grasp or measure directly. It exists as relationships, as the way points, lines, and surfaces operate within a tightly connected system. Space can be flat, positively curved like a sphere, or negatively curved like a saddle. It can be finite or infinite, curling up like a video game map or extending endlessly. To explore it, scientists cannot stand outside the universe to observe. They must observe from within, through how light moves, how galaxies rotate around each other, and how radiation left over from the Big Bang spreads everywhere. This is where the concept of topology emerges. It helps us understand how space is connected, even when we cannot see it entirely. A universe can be flat, but curl in on itself, or curved but extend infinitely. Curvature indicates how space bends. while topology shows how elements of space are linked. These two properties shape how we understand reality, how planets orbit their stars, and how light from distant galaxies reaches our eyes. Therefore, the shape of the universe is not just an intellectual game or a thought experiment. It is the essence of the reality we live in, quietly governing every motion, every orbit, and every cycle. You may walk your whole life on a seemingly flat line, but in reality, you are moving along a vast circle invisible to the naked eye. The shape of space may hide itself, but through careful observation, through science and mathematics, we can trace those invisible lines. And when you next think about geometry, remember that it is not only specific objects that have shape. Even emptiness, the space between objects, has form. It is silent, invisible, yet simultaneously dynamic and flexible. Empty space is not nothing in the usual sense. It is a fabric on which the universe weaves physical laws, a stage on which every planet, star, and galaxy plays its role. Imagine that you are drifting in deep space where no planet or nearby star glimmers. No up, no down, no sound, no wind. Only silence and distant stars like faint, scattered points of light. There, you release a marble from your hand. It does not fall as it would on Earth, nor is it pulled by any invisible force. Instead, the marble moves along the path that space-time has curved around you. This is the subtle nature of gravity according to Einstein's theory. It is not a pulling force, but the result of curvature in space-time. On Earth, we experience this every day without realizing it. Every step you place on the ground, every object falling from above, reflects how the space around you is shaped. But on a cosmic scale, this becomes far more magnificent. Stars, planets, and galaxies do not merely exist in space. They bend it, creating dents that other objects naturally follow. A simple visual example is to imagine a stretched elastic sheet. When you place a bowling ball on it, the sheet sags. Any marble rolling on the sheet curves toward the depression, not because the ball pulls it, but because the surface has deformed. In the universe, that sheet is space-time, and planets, stars, or even light all move along those curves. This effect is not just a metaphor, it is observed in reality as gravitational lensing. When light from a distant galaxy passes near a massive object such as a galaxy cluster or black hole, the light bends, appearing from multiple angles. The result is that background galaxies appear magnified, bent, and even multiplied, allowing astronomers to observe regions of the universe too distant to see with ordinary telescopes. Gravitational lensing is not only a physical phenomenon, it is living proof that space itself has shape, structure, and behaves as an active physical object. Curved space also changes the way we understand distance and time. In a flat universe, the shortest path between 2 points is a straight line. But in curved spacetime, this line becomes a geodesic, the natural shortest path in curved space. When you fly in an airplane on Earth, you have seen this. Flight paths on the map appear curved, but in reality, they are the shortest route over the curved surface of the planet. Now imagine this happening in three-dimensional space plus time as a fourth dimension, and you will realize that all objects, from planets to light, move along curves created by space-time. But it is not only light or planets that are affected. Time is also curved. Clocks run slower in stronger gravitational fields, a phenomenon called gravitational time dilation. This is not science fiction. Experiments with ultra-precise atomic clocks have confirmed it. A clock placed on a mountain where gravity is weaker runs faster than one at sea level. Even the GPS system we use daily must be adjusted according to relativity to provide accurate positions. Without this, your phone could be off by kilometers in just a single day. This proves that the geometry of space, though invisible, directly affects our lives. Empty space, the void, is not a passive stage. It acts, vibrates, expands, and bends. In 2015, humanity detected gravitational waves for the first time, ripples in space-time traveling at the speed of light, originating from two black holes colliding more than 1 billion light years away. These extremely tiny vibrations shook instruments on Earth, proving that space itself is a dynamic entity with shape and motion. The geometry of the void is not an abstract concept. It operates and produces tangible effects, even if we cannot perceive them with ordinary senses. The 1919 solar eclipse experiment led by Arthur Eddington is another classic example. By observing stars near the edge of the sun, he found light bending as predicted by Einstein, confirming that mass can curve space-time. Since then, a series of astronomical phenomena, from the motion of planets and moons to distant light, have all been explained by space-time geometry. Space is not a simple, empty concept. It is an entity with structure, rules, and the ability to shape everything. Imagine standing in the infinite void with no light and no strong gravity. The marble you release does not fall, but if you move near a planet, it will naturally follow the curve created by spacetime. This is why gravity is not a force in the traditional sense, but a property of the geometry of the universe. From Newton to Einstein, we have moved from understanding gravity as an abstract force to recognizing it as a curve, a shape, a fundamental property of reality. And when you look up at the sky, seeing distant light from primordial galaxies, remember that it travels through a living space, curved by surrounding matter, woven by gravitational waves, and shaped by the overall structure of the universe. The geometry of the void is not just a mathematical game, it is the essence of the universe, governing every motion, every orbit, and even the passage of time. Even if you cannot see the entire cosmos, every measurement, every observation is a step closer to understanding the grand stage we live on, where every star, every galaxy, and every ray of light dances along the invisible curves of spacetime. Imagine you are standing on the shore of an invisible ocean where the stars are silently floating buoys, and space is the water, full of life that you cannot see. Every time you inhale, you breathe in a part of the expanding universe. The distant stars, galaxies flickering in ancient light, are not stationary. They are drifting apart, not because they want to, but because the fabric of spacetime itself stretches and expands. This is the deepest essence of the Big Bang. It is not the galaxies that shoot out like fireworks, but the space between them expanding, every second, every minute, silently yet surely. The idea that the universe is expanding may be hard to imagine, but there are clear signs. Light from distant galaxies not only reaches us later, but is also redder, stretched into longer wavelengths. This is the cosmic redshift effect, undeniable evidence that the distance between us and those galaxies is increasing. And when we look at the cosmic microwave background radiation, the ancient echo of the Big Bang, we perceive a subtle picture of the distribution of matter and energy in the early universe. Small fluctuations in this radiation are like wrinkles on the surface of spacetime, revealing dense regions and voids that later became galaxies and galaxy clusters. But space does not only expand, it also bends. Black holes, objects of extreme mass, curve spacetime so strongly that nothing can escape, not even light. When a massive star collapses, it forms a black hole, a chasm in the universe where spacetime itself becomes an invisible barrier. These black holes, once thought to be bizarre on paper, are now confirmed to exist, from the centers of galaxies to remote regions of the cosmos, spinning invisibly, silently absorbing everything around them. In 2019, the first image of a black hole was released, a dim ring of light surrounding an impenetrable dark center, allowing us to directly experience Einstein's equations come to life. It does not stop there. In 2015, humanity heard the echoes of the universe for the first time through gravitational waves, ripples in space-time caused by the collision of massive black holes. These waves stretch and compress space in extremely subtle ways, enough for instruments on Earth to detect distortions smaller than a proton. The idea that space, seemingly invisible void, can ripple like water still amazes us. Each such event is a message from extreme cosmic catastrophes, echoing through the vast emptiness, reminding us that space-time is a living entity, not a blank backdrop. All these phenomena, bent light, time dilation, planetary orbits, black holes, gravitational waves, originate from a single law. Mass and energy curve spacetime, and the shape of spacetime guides how objects move. It is a perfect circle. Space and matter are tightly linked, like a graceful dance that Einstein predicted over a century ago. However, general relativity is still not the complete story. On the microscopic scale inside atoms, it collides with quantum mechanics, the other great theory of the natural world. Unifying these two frameworks is one of the greatest challenges of modern physics, but this does not diminish the remarkable value that general relativity provides. It remains one of the most beautiful scientific theories, combining mathematical precision with profound philosophical insight. One of the most fascinating aspects is the overall shape of the universe. Is space flat, curved inward like a sphere, or curved outward like a saddle? In a flat universe, parallel lines always remain parallel, and cosmic triangles still add up to 180 degrees, just like on paper. A closed universe with positive curvature is an endless loop. Go far enough, and you return to your starting point. An open universe with negative curvature like a saddle stretches infinitely, expanding forever, never repeating, cold and empty over time. To measure the shape of the universe, scientists observe ancient light from the cosmic microwave background, the afterglow of the Big Bang. Subtle fluctuations in this radiation indicate how matter was initially distributed and predict whether space is flat, curved, or open. Analysis of data from satellites such as COBE, WMAP, and Planck shows the observable universe is nearly flat, but this is only within the limits of our observations. Beyond the observational horizon, space may still bend, ripple, or twist mysteriously. This leads to a profound question: why is the universe nearly flat? This balance is extremely delicate. If the energy density were slightly higher, the universe would collapse. Too low, it would disintegrate too quickly. A plausible solution is the theory of cosmic inflation. Immediately after the Big Bang, the universe expanded extremely rapidly, smoothing out all wrinkles and curves, creating a homogeneous, vast, and nearly perfect space. Yet, the universe still holds many mysteries. Space may bend subtly in ways we have not yet detected. It may contain strange structures or be part of a multiverse, where different patches of spacetime have their own curvature and dimensions. Even silence becomes structured. Even the void is architecture. And it is this grandeur that makes us look up at the night sky, realizing that every star, every galaxy, every beam of light dances according to the invisible, subtle, and perfect geometry of spacetime. When we look up at the night sky, what amazes us is not the absence of light or the enveloping darkness, but the realization that everything we see is drifting away, endlessly expanding in the infinite space. Each star, each galaxy that the naked eye perceives, is only a fragment in the vast picture that we have never seen in its entirety. We are passengers on an invisible spaceship, traveling through the sea of spacetime, drifting along the gentle but steady rhythm of expansion. The universe is expanding, and with every moment, the distance between galaxies increases by centimeters, by millions of light years. Yet this does not change our familiar world. Earth remains intact. Your body is not stretched, because gravity, electromagnetic forces, and nuclear forces hold everything together. Expansion only becomes noticeable when we look far enough to distances where gravitational attraction is no longer strong enough to hold galaxies together. The universe is not only expanding, it also carries subtle clues about shape and structure. Imagine ancient light, the cosmic microwave background radiation, traveling through space for nearly 14 billion years. It is a message from the past, a snapshot of the universe when it was still in its infancy, when matter was just beginning to arrange itself into clouds, galaxies, and the first galaxy clusters. Tiny fluctuations in density and temperature in this radiation are like wrinkles on a fabric, revealing how gravity began to pull galaxies together, while simultaneously giving us a glimpse of the overall shape of space. That is why scientists can talk about a flat, positively curved, or negatively curved universe. If the universe is flat, parallel lines maintain their distance forever. Triangles have interior angles summing to 180 degrees, and light follows stable trajectories without bending beyond local gravitational fields. If the universe is positively curved like a three-dimensional sphere, light from ancient fluctuations converges, making patterns in the background radiation appear larger than predicted. If the universe is negatively curved like a three-dimensional saddle, light diverges and the patterns appear smaller. Each measurement, each observation is like decoding an intricate message that the universe sends us, reminding us that space and time are not mere foundations, but silent storytellers, guiding every event and every life. But determining the shape of the universe is not just a geometric exercise. It is directly related to the fate of the cosmos. A closed universe with positive curvature might stop expanding and begin to contract, leading to a reverse Big Bang or Big Crunch. An open universe with negative curvature will expand forever, becoming ever colder and emptier as galaxies drift apart and their light fades beyond reach. A flat universe, as recent measurements indicate, is delicately balanced, expanding indefinitely but at a steady rhythm. This balance is extraordinary. If the density of matter and energy were slightly higher, the universe would collapse. If slightly lower, it would disintegrate too quickly. Everything must be just right to allow galaxies, stars, and life to form. This is the miraculous fragility of nature, where delicate equilibrium keeps the universe in an almost unbelievably perfect state. What makes everything even more wondrous is the phenomenon of cosmic inflation. Immediately after the Big Bang, the universe underwent a period of extremely rapid expansion, faster than the speed of light, yet not violating relativity because space itself expanded rather than matter moving through space. This enormous expansion smoothed out all wrinkles and minor curvatures, making the universe flat and homogeneous in a broad sense. That is why, when observing the cosmic microwave background, scientists see a remarkably uniform pattern, despite the vast distances and enormous separations between galaxies. But expansion did not stop there. In the late 1990s, observations of supernovae revealed that the universe is accelerating in its expansion. A mysterious force called dark energy, accounting for roughly 70% of the total energy of the universe, seems to push galaxies apart faster over time. We do not know exactly what dark energy is. It emits no light, has no fixed mass, yet appears to be a pressure woven into the fabric of space-time itself, causing the universe to expand at an increasing rate. This presents a strange prospect. Distant galaxies will gradually disappear from our view, their light never reaching our eyes, creating a cosmic event horizon, the ultimate limit of what we can observe. From this perspective, we realize that space and time are not fixed. They evolve, expand, and bend according to the subtle laws Einstein predicted. Each of us is a passenger on this vast, evolving stage. Every beam of light, every galaxy, every small fluctuation in the cosmic microwave background tells the story of a living, evolving, and exquisitely flat universe. The universe is not only vast, it is arranged according to exquisite geometry, where straight lines are truly the shortest distance between 2 points. Triangles have interior angles summing exactly to 180 degrees, and geometric rules operate even when we observe from billions of light years away. In a flat, infinite, and boundless world, we do not merely observe, we learn to read the shape of space, not on paper or drawing boards, but in the stars, in light traveling through time, in the subtle wrinkles the universe has recorded over 14 billion years. Each measurement, each observation, each tiny fluctuation is a step forward in humanity's journey of understanding, bringing us closer to decoding one of the deepest mysteries, the true nature of spacetime, the shape and fate of the entire universe. When we observe the vast tapestry of the universe, a feeling both overwhelming and gentle seeps into the mind. The universe, in its infinite immensity, maintains a nearly perfect balance. Data from the WMAP and Planck missions have allowed us to measure the tiniest fluctuations in the cosmic microwave background radiation with unprecedented precision, and the results are astonishing. Our universe is almost flat, but this is almost flat, not absolutely flat. Imagine a gigantic pancake stretching across billions of light years, where even the smallest curvatures are nearly imperceptible. Or, if the universe were perfectly flat, this would imply something extraordinary. Its total energy density must lie exactly at the critical level, the delicate balance point between endless expansion and the risk of collapsing into a universe-wide implosion. This critical density is a subtle concept. If the universe contained too much matter, gravity would dominate, pulling all the galaxies back together, eventually leading to a big crunch. If there were too little matter, gravity would be insufficient to restrain the expansion, and the universe would expand forever, growing colder and emptier. A flat universe lies precisely between these extremes, expanding forever, yet step by step, moment by moment, approaching a stable rate. A cosmic rhythm so perfectly balanced it seems miraculous. And this is the mysterious story that cosmologists face. When they calculate the amount of matter and energy in the universe, only about 5% is ordinary matter stars, planets, dust, gas, even black holes, not enough to the critical density. Dark matter appears as an unexpected answer. Invisible to direct observation, it is detected only through the gravitational force it exerts, adding roughly 27% to the total energy needed. Yet 68% remains missing, and that is when dark energy enters the story. Dark energy is a mysterious pressure woven into the fabric of spacetime, pushing galaxies apart and accelerating the expansion. When ordinary matter, and dark energy are combined, the universe's total density seems to match the critical density almost perfectly. A stunning precision, like throwing a blindfolded dart from thousands of miles away and hitting the bullseye. This balance raises profound philosophical questions. Why is the universe so precisely flat? Is it a mere coincidence or the result of a deeper physical law yet to be discovered? One of the most plausible theories is cosmic inflation, a period of extremely rapid expansion immediately after the Big Bang. In this brief moment, any initial curvature would be smoothed out, much like inflating a balloon until all dimples disappear. Inflation acts like a cosmic iron, flattening spacetime into an almost perfect sheet. If this theory is correct, it explains why the universe today appears flat, even if it initially was not. However, living in a flat universe brings no sense of strangeness to everyday life. Planetary orbits, galaxy motions, and ancient light trajectories all behave as expected. Unless extremely precise measurements are taken, you would notice no distortions. There are no invisible walls, no points causing you to circle when walking straight. Flat space offers a sense of normalcy, yet its implications are extraordinary. A flat universe can be infinite. You could travel in a straight line forever, never returning, never encountering a boundary or center. Every point is equal, a profound cosmic symmetry. Yet all observations are limited by our observable horizon. Beyond it, space may curve slightly or even loop into a finite but flat structure, like a video game map where exiting one side brings you back to the other. Even in its simplicity, flatness provides a crucial clue. Space is an active, measurable structure, and geometry is not only a tool for architects or artists, it is the foundation of existence. This flatness also opens a strange perspective. Imagine walking along a perfectly straight path through galaxies, nebulae, cosmic dust, and comets. You could travel for billions of light years and potentially return to your starting point without turning around. This is the possibility a closed, finite, yet boundless universe provides. A straight line, called a geodesic, eventually meets itself. Triangles have angles summing to more than 180 degrees, and parallel lines ultimately converge. These seemingly minor geometric changes directly affect how light travels, how galaxies distribute, and how the universe evolves. In general relativity, energy density, matter, radiation, dark matter, and dark energy determines the shape of the universe. If density exceeds the critical level, space curves inward, forming a closed universe. Gravity is strong enough to slow the expansion, even reverse it, leading to a big crunch, where everything collapses back into a dense hot point, potentially starting a new cycle. On small scales, the solar system, galaxies, curvature is negligible, but when connecting points across billions of light years, the overall shape becomes apparent. Cosmologists seek clues through the cosmic microwave background. In a closed universe, light converges with large angle fluctuations greater than predicted. The large-scale distribution of galaxies also reveals subtle curvature patterns. Recent measurements, especially from the Planck satellite, show the universe is very nearly flat, yet there is room for slight positive curvature, a subtle clue, both challenging and captivating. In cosmology, the subtlety lies in simplicity. A flat universe, a balanced universe, a universe where physical laws operate perfectly across infinite distances. And within this flatness, we recognize every observation, every measurement, every ancient beam of light is a reminder of the delicate arrangement of existence and our place in the grand cosmic tapestry. In an open universe where space stretches infinitely like an endless hyperbolic surface, we begin to realize that eternity is not merely an abstract concept. It is a direct reality, a law governing how light, matter, and time operate. The hyperbolic geometry of this universe is not a fantasy. It is an inevitable consequence of the overall energy density being below the critical level. On small scales, everything still seems normal. Planets orbit stars, galaxies maintain their shapes, and light appears to travel along familiar straight paths. But when you extend your view across billions of light years, you see that all straight lines truly diverge. Large triangles have angles summing to less than 180 degrees, and parallel lines never meet. In an open universe, everything is larger than intuition allows, distance, time, space, and this forces the human imagination to reach a completely new level. And within that divergence, the light becomes a message from the past. The cosmic microwave background radiation, or CMB, is the remnant from the moment the universe was only 380,000 years old. This was when the hot, dense, chaotic plasma transformed into a transparent space, allowing photons to travel freely. Those photons, after more than 13.8 billion years, are still streaming across the universe, carrying clues about the shape, structure, and history of all that exists. Each tiny temperature fluctuation in this radiation is a subtle indicator of matter and energy density, of expansion, and of the geometry of space. In an open universe, these fluctuations are slightly smaller than expected, reflecting the diverging paths of light and stretching beyond what human senses can predict. Imagine holding a telescope powerful enough to see those photons. You are not merely observing the light of stars, but the light of the early universe, a pristine, cold, yet gentle portrait, preserving every detail from before the first galaxies formed. In that moment, time seems to flow backward, and you become a witness to the transformation from a sea of hot plasma to a vast, complex, multi-layered universe. This is not an illusory experience. It is a reality science allows us to reach through extremely precise instruments and measurements. In this vast picture, each galaxy becomes an isolated island amid a dark, infinite sea. As the universe expands, the distances between them grow, and eventually the light from one galaxy can no longer reach another. Communication becomes impossible, and observation becomes limited. This scene, though seemingly bleak, carries a tranquil beauty. The slow but steady expansion, the diverging spaces opening infinitely, creating a realm both vast and mathematically precise. It is a universe where freedom exists in the absolute sense. Every point, every direction is an unexplored opportunity. Hyperbolic geometry affects not only the path of light, but also the distribution of matter and energy. In an open universe, gravity is insufficient to reverse the expansion. Galaxies drift apart, stars gradually exhaust their fuel, and solitary black holes become the final markers in a fading sky. Over time, the sky may become completely dark, not due to destruction, but simply because everything drifts beyond view, quietly merging into the void. This is the so-called heat death, a non-dramatic yet profound end, where entropy reaches its maximum and the universe enters a state of stillness and uniformity. Yet the beauty of an open universe lies in this. Infinity does not mean emptiness. It is an intellectual playground, a challenge for the imagination, where every direction is a new path, every expanse of sky a mystery yet to be decoded. The universe imposes no boundaries, no forced enclosure, but expands every possibility. Even if we cannot access everything, the idea of infinite space allows us to realize that the potential for exploration and understanding is limitless. Interestingly, hyperbolic geometry also appears on small scales in art and nature. Infinite repeating patterns, complex curves in coral, lettuce leaves, or Pringles chips all reflect the same principles as saddle-shaped space. This reminds us that the laws of the universe are not only abstract, but also manifest visually in the world around us. And on a cosmic scale, an open universe directly impacts time. It stretches endlessly forward, with no stopping point, no final shock, only the continuous flow of space and time. The story of the open universe, with hyperbolic geometry and the CMB as evidence, is a reminder that space is not a passive void. It is a living, structured entity with boundless freedom. Every diverging line, every tiny fluctuation of background radiation tells the story of expansion, of freedom, and of limits beyond human intuition. In this picture, humans are not the center, but attentive observers, capable of recognizing balance, order, and the limitless vastness of the cosmos. Finally, when we look up at the night sky, what exists is not only twinkling stars or distant galaxies. What exists is also a vast, endless, and silent story of space, time, and ancient light. Every CMB photon, every tiny fluctuation, every infinite void reminds us that the universe expands not only in space, but in the potential for knowledge, imagination, and the wonder humans can experience. A saddle-shaped universe is not a place of loneliness, but a place where freedom and potential exist in the deepest sense, inviting us to embark on unprecedented journeys and to see the universe in both its cold and miraculous beauty. As the ancient light of the universe quietly spreads across the sky, we are not merely observing tiny temperature fluctuations in the CMB, we are reading a map written in the very history of the cosmos. Each bright point, each small bump and dip, is a trace of differing densities in the primordial plasma, a moment before the universe had cooled enough for light to travel freely. These fluctuations, seemingly insignificant, actually contain crucial answers about the overall geometry of the space we inhabit. When astronomers analyze them, they do not just see bright spots. They are constructing enormous cosmic triangles with edges stretching across billions of light years and angles defined by the paths of light from the primordial plasma to telescopes on Earth. It is thanks to these seemingly abstract triangles that we can begin to understand curvature, bending, and whether space is flat or curved. In this process, a subtle picture gradually emerges. If the universe is flat, the sum of the angles of these cosmic triangles will be exactly 180 degrees, as we learned in Euclidean geometry in high school. If space is positively curved like a sphere, the angles add up to more than 180 degrees, causing the cosmic triangles to bulge. Conversely, if space is negatively curved like a saddle, the angles are less than 180 degrees, and the triangles spread out in a way that ordinary intuition can barely imagine. But the miracle is that observations from satellites such as COBE, WMAP, and Planck show that these triangles are nearly perfect. The angles sum to exactly 180 degrees, or deviate only slightly. This indicates that on the largest scales we can observe, the universe is nearly flat, a marvelous balance created by nature, leaving humans in awe of its astonishing precision. But that flatness does not mean simplicity. The tiny fluctuations in the CMB reveal a diverse picture of the primordial matter density. Some regions, slightly denser than their surroundings, became the seeds of galaxies, galaxy clusters, and the cosmic web. These subtle temperature wrinkles are the seeds of all the large-scale structures we see today, from distant spiral galaxies to the quiet planets in our solar system. Each photon in the CMB carries information about those seeds, a 13.8 billion year old record that only the most sophisticated instruments can decode. When we look at the CMB, we are not merely observing light, we are observing history. We see traces of sound waves propagating through the hot plasma, the recombination of protons and electrons, and the birth of free light. This picture acts like a ruler stretched across the sky, a ruler where any deformation in the geometry of the universe would make the features appear larger or smaller than expected. This is the measurement of the angular diameter distance, a highly precise yet remarkably intuitive tool. When scientists apply this method, they are using the light of the universe as the most accurate measure to determine whether our space is flat, positively curved, or negatively curved. The astonishing fact is that thanks to missions like Planck, we now have extremely detailed data showing the universe is nearly flat. But nearly flat does not mean empty or meaningless. This balance also reveals another secret: the ratio of matter and energy in the universe. Ordinary matter accounts for less than 5%, dark matter about 27%, and the majority, approximately 68%, is dark energy, which we still do not fully understand. The delicate combination of these three components creates an overall density that is nearly ideal, making space appear flat on cosmic scales. This is extraordinary. A universe that can stretch infinitely yet maintain an almost perfect balance, where all components cooperate to produce its present shape. One proposed explanation for this flatness is inflation, the period of exponential expansion in the first moments of the universe, flattening any initial curvature. But beyond the formulas and data, the CMB is also an emotional marvel. These photons have traveled through space from before the Earth formed, before the sun rose, and even before the first galaxies appeared. They remain here as silent messengers from the past, quietly telling the story of the moment the universe emerged. When we fine-tune our instruments to hear them, we do not hear sound, but patterns, tiny fluctuations rich with information, guiding us toward answers about the universe's shape and history. These measurements are not just mathematics. They are a connection between past and present, between ancient light and modern observation. Each cosmic triangle, each tiny temperature fluctuation is a piece of the largest puzzle. What shape is the universe and how does it operate? From these abstract concepts, humans find subtlety, beauty, and astonishing harmony in nature. We learn that the universe, though vast and seemingly infinite, operates according to logical, measurable laws, and within its nearly perfect balance holds its deepest secrets. Ultimately, looking at the CMB is looking into the very nature of the universe. This is quiet, ancient, fragile, yet persistent light, guiding us through the largest questions about space, time, matter, and energy. When physicists measure the angles of cosmic triangles, when they analyze the tiniest fluctuations of the CMB, they are seeking answers to one of the greatest questions. Is this universe flat, positively curved, or negatively curved? And the nearly perfect result, the angles summing to exactly 180 degrees, gives a magical sense of certainty that, even on cosmic scales, the universe has logic, order, and can be understood by human intellect. In that vastness, the cosmic triangle becomes a symbol. Only three sides, three angles, yet containing the entire story of the universe's shape. And thanks to the CMB, the light from 13.8 billion years ago, we can read that story, perceive the balance, the flatness, and the absolute beauty of a universe humanity is still gradually discovering. The space around us, though it appears flat and infinite, may conceal subtle mysteries that only light and mathematics can reveal. When we say the universe is nearly flat, it does not mean completely eliminating curvature. On cosmic scales, any curvature, if it exists, is extremely small, about 1% or less, a number that seems negligible, but is enough that the most sophisticated instruments in human history must exert their utmost effort to detect it. It is this subtlety that makes each measurement a journey of discovery, where light becomes the most faithful messenger, carrying hidden messages from the universe's earliest moments. Light never travels perfectly straight. Along its path, it must pass through galaxy clusters, vast voids, and dark matter fields, all of which gently bend its trajectory, an effect scientists call gravitational lensing. These distortions make measurements more complex, but also richer. We might imagine this as reading a signboard under dazzling sunlight. The message is still there, but the light vibrates along its journey, creating a vivid map of how space operates. The triangle test, simple in concept, becomes a powerful tool for probing cosmic geometry. Just three sides, three angles, yet it encapsulates the entire story of the shape and structure of space. But triangles are not only a tool for the CMB, they open a geometric language for exploring other aspects of the universe. For example, by comparing the brightness and redshift of supernovae, astronomers can estimate cosmic distances and expansion rates. When combined with measurements from the CMB, supernovae, and galaxy distribution, we build a comprehensive picture where each is a piece of the puzzle. Each piece brings us closer to understanding the overall shape of space, a gigantic geometry that no blackboard in school could contain. On the largest scales, spatial geometry becomes magical. Shapes we once considered simple, like triangles, can probe the entire universe. It reminds us that ancient tools from Euclidean geometry still hold astonishing power. No need for bulky particle accelerators or extraterrestrial instruments. Sometimes a triangle and ancient light are enough to open a door to the deepest understanding. And this leads us to another fascinating realm, topology. Topology does not care about lengths or angles, but focuses on how elements of space are connected. A coffee cup and a donut, from a topological perspective, are the same. A single hole can transform one object into another without cutting or gluing. Applied to the universe, this raises a subtle question. How is space connected? Could you travel straight forever and return to your starting point? Not because of curvature, but because of its intricate connectivity. The universe can be flat, yet still repeat in mysterious ways. A simple example is a two-dimensional square. If you glue the left and right edges together, the square becomes a cylinder. Glue the top and bottom as well, and you have a torus, a donut. An ant crawling on this surface would return to its starting point, even though the plane persists. Scaling this to 3 dimensions, we can imagine a three-dimensional universe with a three-torus structure, finite but without boundaries. This is one way scientists conceive of cosmic topology, where spatial dimensions are sewn together intricately. If space repeats, light can travel along multiple paths and arrive at the same point multiple times. A distant galaxy may appear not just once but several times, like reflections in a mirror, creating faint patterns in the sky. Cosmologists have searched for signs of this phenomenon in the CMB, such as repeated circles or symmetrical patterns. So far, no definitive evidence has been found, but that does not rule out the possibility. The universe may be repeating on scales beyond our observational horizon, where light has not yet reached us, or the repeating signatures may be too subtle to detect. This possibility is not merely abstract mathematics. It profoundly affects our understanding of matter, energy, entropy, and the universe's future. A finite yet boundless universe, folded through subtle connections, changes how we think about entropy. Total energy and matter are no longer infinite but finite in a structured way. Some models even suggest traces of inflation. The rapid early expansion may have locked in this structure, like a scar from the moment of the universe's birth. The sensation of living in a multi-connected universe is thrilling. You could look far away through a telescope and, in theory, see yourself from billions of years ago, not via a mirror, but through light traveling around the universe. Though theoretical, it evokes a spectacular vision. Light, matter, and space connected in ways far beyond everyday intuition, forming a delicate map of cosmic connectivity. Topology reminds us that shape is not just curvature, it is how everything connects, loops, and continues. A flat universe can still be twisted through structure. An apparently infinite universe can be finite through subtle connections. Shapes like donuts, loops, and complex symmetrical patterns are wonderful metaphors, helping us visualize what cannot be seen directly. In this world, light and triangles become a language. Topology becomes a lens for observation, and imagination becomes the tool to conceive limitless possibilities. The universe may be finite or infinite, flat or curved, but one thing is certain: its connectivity, the silent loops, and intricate shapes are waiting for us to explore, one photon, one triangle, one spiral at a time. And it is within these connections that we find the quiet yet magnificent beauty of space, where science, mathematics, and imagination converge. If you try to imagine yourself as a traveler wandering through the universe, you will realize a marvel. Every direction you go ultimately leads back to your starting point. Not in the way ordinary intuition suggests, like when you turn around and see the mountains appear as before, but according to a deeper, more subtle logic, where flat and finite space coexist simultaneously. A toroidal universe, a universe geometrically flat in the Euclidean sense, illustrates this beautifully. On a small scale, triangles are still triangles. Parallel lines do not meet, angles add up as they should, but overall, this space is multiply connected. You traverse its full length and reappear exactly where you began, as if the space has been sewn neatly and discreetly. This idea is not unfamiliar to us when looking at virtual worlds. A looping video game map or a small mirrored maze has given us a taste of a space where boundaries no longer hold their usual meaning. You can walk forward endlessly without ever encountering a final wall, and every direction becomes a path leading you back to the starting point. This is the logic of an intelligent space, not curved like a balloon, but enclosed and connected according to an order invisible to the eye. And if a torus is a typical example of simple connectivity, the universe contains even stranger shapes. The Mobius strip with a single surface evokes the concept of reversed orientation. An insect crawling on it would traverse every point without leaving the surface, returning to the start with its orientation reversed. Extending this concept into three spatial dimensions introduces a wondrous possibility. Space can not only repeat, but also invert subtly. Imagine sending a spaceship on such a journey. It returns to its original position, but everything within it is reflected quietly, like a play of light and shape. Moreover, there are structures like the Klein bottle, a seemingly paradoxical surface where inside and outside merge. It cannot hold water conventionally, but this theory illustrates the imaginative power of topology. Space can be rolled, twisted, and folded, yet remain continuously connected. Though it sounds like magic, these ideas stem from the same mathematics that help us visualize the donut or moving ribbons, opening new possibilities for cosmic structure. For a more intuitive example, return to the game map, Pac-Man, where opposite edges are connected. You leave the screen's edge on one side and appear perfectly on the other, a smooth, borderless movement. This is not just a game, it is a candidate model for the universe's connectivity. Such a universe could be finite in volume but boundaryless, with no walls to collide with. Space is closed, continuous, twisting in ways the human mind struggles to grasp. Discovering these loops in reality is an extraordinary challenge. Astronomers search for repeating patterns in the cosmic microwave background, structures mirrored across opposite regions of the sky. They observe the paths of light, hoping to detect duplicate images of the same galaxy from multiple directions. So far, no definitive evidence has emerged, but that does not negate the possibility. These loops may extend beyond our observational limits, like fish in a pond unaware that the water curves in ways they cannot perceive. The sensation these loops evoke is wondrous. The universe becomes infinite but not unbounded, like a continuous flow without waste, corners, or edges. It does not expand out of control, but quietly coils snugly and perfectly. Topology presents a picture of the universe as an intricately woven tapestry. Points, lines, and loops interlace to form a strong and harmonious structure. This is logic, structure, not chaos. Even the strangest shapes obey consistent rules, a silent harmony that science gradually uncovers. Imagine the winding paths of light, curving through spatial loops, carrying messages across billions of years. Though you never touch a boundary, the experience evokes a sense of infinity, for the universe is self-contained yet vast. Each photon, each triangle, each loop is a symbol astronomers learn to read to understand the overall structure. It is not absurdity, but the high-level logic of three-dimensional space. Intuitively, we can picture it as walking on Earth. You move straight north, then return, circling the planet without ever falling off. Apply this logic to three dimensions, and you see a universe finite in volume but infinite in travel possibilities. Space curves, closes upon itself, coils upward, and moving through it gives a sense of both infinitude and safety. Finally, this observation extends to philosophy. The universe has no center as we imagine. The Big Bang did not occur at a single point, but everywhere at once. Each point in space is the center of itself, a uniform experience for every observer. Space expands, but not into emptiness. It expands within itself. This renders the notions of boundary, center, or edge ambiguous, and it is where science, mathematics, and imagination converge to envision reality. The universe, in all its complexity and subtlety, is a harmonious combination of structure, logic, and aesthetics. From small loops to macroscopic loops, from Mobius strips to tori, from light passing through the CMB to the imagined paths of spaceships, all tell a story of a connected, delicate, and elegant space, a universe that can be finite yet in no way constrained. Imagine standing in a vast space where time and light intertwine, and every point in the universe becomes the center of itself. The observable cosmic bubble that we can see, with a radius of about 46 billion light years, is a vivid picture of the past and the present simultaneously. Each photon we observe today began its journey billions of years ago. Some light departed from galaxies before Earth even formed, while others were emitted when dinosaurs still roamed this planet. All these rays travel through expanding space, stretched, yet still carrying information about the original structure, matter, and energy. And no matter which direction you look, your view is limited, not by a wall, but by the time light must travel to reach you. This is the observable universe, a spherical bubble surrounding you, containing everything that light can bring from the past. The observable universe is a display of a much larger whole, possibly infinite, far beyond human observation. Distant galaxies, faint galaxy clusters, light paths stretched into microwaves all tell the story of a continuous, unified, and enclosed space. Yet the most fascinating aspect is not just what we see, but what we cannot see. If the observable universe is a sphere of light, the rest of the universe, beyond the horizon of observation, may contain entirely different galaxy structures, strange arrangements of matter, or subtle variations in matter and energy density. This is not science fiction. It is a direct consequence of cosmological principles, which posit that the universe is homogeneous and isotropic on large scales. We are not at the center, and every observer at any location experiences their own cosmic bubble. The expansion of space complicates the notion of boundaries. Distant galaxies are moving out of our view at speeds exceeding that of light, not because they travel faster than light, but because the space between us and those galaxies is expanding. This is the cosmic event horizon, a boundary that cannot be crossed, not a physical wall, but a mathematical limit that light cannot surpass. Regions beyond this horizon still exist, but we will never reach or observe them. In a philosophical sense, this evokes humility. Even with the most advanced telescopes and all modern instruments, the universe keeps a portion of mystery for us, a domain that humans can only imagine. And if the observable universe is like this, then the total universe, the part we have not and cannot observe, may be thousands, millions, or even billions of times larger. Some modern theories suggest that space may be curved closed like a three-dimensional torus or extend infinitely. In universes with special topologies, a traveler could end up where they began without ever touching a wall. Light from distant pasts could travel multiple paths, creating duplicate copies of galaxies. This is where mathematics and imagination meet, where physical principles combine with geometric logic to create possibilities beyond human intuition. Even more astonishingly, considering early cosmic inflation, space did not merely expand. It underwent rapid bursts, flattening all curvature, smoothing out all density irregularities. This inflation may not have occurred uniformly everywhere, leading to the concept of a multiverse. Newly formed regions containing sub-universes with their own laws of physics, densities, and structures. This is not science fiction with parallel dimensions or alternate versions of humanity. It is a natural consequence of modern mathematics and physics, regions of space-time from which light will never reach us. Meanwhile, the observable universe is our practical laboratory. We can map galaxies, observe dark matter through gravitational lensing, even reconstruct spatial geometry through ancient light. We do all this while knowing that only a tiny fraction of the total is displayed before our eyes. Most fascinating is that the universe appears homogeneous and isotropic. From every direction, it looks the same. This is the basis for the assumption that the unseen remainder also follows the same physical laws, though there may be subtle variations. The combination of the observable universe and regions beyond our view creates an awareness that is both humbling and majestic. We will never see the entire universe, yet each step of observation reveals delicate order. Every ancient photon, every galactic orbit, every fluctuation of the cosmic microwave background is part of the long story of a space that is closed, infinite in experience, but finite in volume. And within this limitation, we recognize the absolute beauty of the universe, a place where boundaries do not exist. Limits are only observational, and continuity, unity, and harmony are what truly matter. So when someone asks you, where is the edge of the universe? You can smile. The answer is not on the other side of the screen, but space does not require boundaries. We live within a self-contained continuum where each observer has a unique perspective and the entire universe continues to expand, weaving untold stories, lights yet to arrive, and infinite mysteries awaiting our imagination. In the silent darkness of the universe, we stand before a space so mysterious that even imagination struggles to encompass it. The observable universe, with more than 2 trillion galaxies, each containing hundreds of billions of stars, is only the tip of a much larger picture. It is not only vast, but also so rich that a human lifetime could never explore it fully. Each galaxy, each star, each planet is a reminder of the universe's wonder, a gigantic theater staging plays that humans can only faintly witness from the edge. When you gaze up at the night sky, you are looking through 13.8 billion light years. Each photon is a messenger from the past, a story of light recounting the distant epochs of the universe, when planets had not yet formed and life had not yet appeared. Yet the true beauty lies not only in what we can see. The rest of the universe beyond the observational horizon remains silent, carrying structures, physical laws, and possibly shapes entirely different from the universe we know. It may be infinite, or it may be enclosed in a marvelous loop. It may exist as one of many universes, each sub-universe with its own laws, creating a vibrant and rich multiverse. And in the silence of these unseen regions, we find a profound humility. No matter how vast our knowledge, there are always mysteries that light has not yet brought to us. Delving deeper into the architecture of space, we encounter strange mathematical entities living quietly in the abstract universe of geometry and topology. The Klein bottle is one of them, a surface without orientation, without inside, without outside. Imagine a tube bent, twisted, connecting one end to the other so that the inside becomes the outside without ever intersecting itself. Something seemingly impossible in three-dimensional space becomes entirely coherent in four dimensions. Klein bottles, Mobius strips, three-dimensional manifolds are not merely mathematical objects. They are windows into how space can operate beyond human intuition. You can map them, calculate their elastic loops, study their connectivity, and realize that the universe may be stitched together in subtle ways invisible to the naked eye. A manifold in mathematics is a space that appears flat at small scales but can be curved, twisted, or folded at large scales. They can be finite or infinite, oriented or non-oriented, closed or open. Some, like the three-dimensional torus, are finite but closed. Others expand infinitely, possibly containing different structures and matter densities. Loops, projection planes, and Plancke polyhedral shapes testify to the diversity and subtlety of these spaces. You follow a straight path, rotate through opposite faces, and eventually return to your starting point, but not in the same direction. We see space not merely as a simple three-dimensional expanse, but as a complex picture, where each loop, twist, and connection has profound mathematical significance. These shapes are not just imagination. They are tools for cosmologists to describe what may occur in the overall structure of the universe. If the universe is finite, it requires a topological structure, possibly closed, twisted, or self-repeating. If the universe has no boundaries, loops and symmetries become necessary to maintain continuity and the coherence of space. These models not only explain how ancient light travels through the universe, but also predict possibilities that future observations might reveal. Matching circles in the cosmic microwave background, galactic orbits suggesting closed or twisted space, or matter variations detectable only by advanced simulations. And although these shapes exist in mathematics, they reflect the strange naturalness of the real universe. The universe does not need to obey familiar shapes we know. No boxes, spheres, or triangles are required to build it. It can bend, twist, close, or be infinite. It may contain higher dimensions we cannot perceive, or be woven with loops and symmetries that only imagination can recognize. Mathematics and cosmology are bridges to understanding these possibilities, subtle tools that allow us to visualize and study a reality that ordinary intuition and senses cannot reach. When you look at the night sky today, imagine standing amid a network of Klein bottles, Mobius strips, and three-dimensional manifolds. Each step, each ray of light, each twisted structure blends together, creating a universe both intuitive and abstract. You do not need to know every detail. Simply recognizing that space can be closed, expansive, and symmetrical is one of humanity's greatest discoveries. Every point in the universe, from the most distant star to the ancient photon reaching your eye, is the center of itself, surrounded by countless possibilities. Space has no boundaries, yet it is full of loops, spirals, and subtle structures that we are gradually discovering. And in this marvelous silence, we learn profound humility. One does not need to be at the center to understand the universe. Every observer from anywhere is the center of their own cosmic bubble. Space expands, galaxies recede, ancient light travels across billions of years, and every loop, every structure, every manifold reminds us that the vastness and subtlety of the universe far exceed any familiar sense of center or boundary. Each night, when we gaze at the sky, we are not merely looking into the past, but also listening to the silent rhythm, the mathematical and physical cadence of a space explored jointly by imagination and science. In the vast expanse of the universe, you can easily feel small, yet simultaneously special in a strange way. As ancient light from distant galaxies travels across billions of years, it brings to your eyes an image of the entire history of the cosmos. Each photon is a message from the past, a reminder that time and space are not static stages. They continuously expand, twist, unfold, and contain surprises beyond human imagination. And because of this expansion, every observer in the universe, regardless of their location, sees themselves at the center of their own observable sphere. From that perspective, galaxies appear to recede in all directions, but this does not make anyone's position more special. Each of us is the center of a personal universe, stretching across space and time, where all ancient light converges upon our eyes. The concept of a traditional cosmic center, where everything revolves like a throne of light, has long vanished. This worldview once made sense in the context of everyday observation. The sun rises, stars rotate, and the Earth seems stationary. But with Galileo, Newton, and later modern astronomers, we learned that the universe has no fixed central point. Our Milky Way galaxy is just one among billions of galaxies. The solar system is only one among countless planetary systems. Earth, with all its familiarity, is merely a tiny speck drifting amidst a sea of galaxies. Yet, in this vast context, human stubbornness still searches for a center, a place to orient oneself, a standing within the cosmos. Interestingly, modern physics gives us an answer both humble and wondrous. The center exists, but not in the classical sense. Every point in the universe is the center of itself, and you at this very moment are gazing from that center. This leads to a subtler discovery. The expansion of space is not merely the movement of galaxies away from each other, but the space itself stretching. There are no enclosing walls, no edge or boundary that light races toward. Every point in space was once compressed during the moment of the Big Bang, and from there, the entire space expanded simultaneously. If imagined the old way, we often picture the Big Bang as an explosion of matter at a single point in space. In reality, the Big Bang occurred everywhere, simultaneously, spanning the entire cosmos. Every point in the universe was once in an extremely dense, extremely hot state, and from that, everything began to spread, creating the modern space we observe today. There is no outside from which to observe, no single starting point. The center is not a location, it is a uniform state, a historical moment propagating throughout the universe. And because space expands in this way, the notion of boundaries or outer walls becomes meaningless. What you imagine as the edge of the universe, a dark wall or a radiant curtain separating the observable from the void, is merely a product of intuition. Just as when standing on a beach, you see the horizon, but as you move closer, the horizon moves with you. It is not a true boundary. The universe works similarly. Observational models and physical equations show that space can be infinite, extending endlessly in all directions or finite but closed, like the surface of a three-dimensional sphere. In the closed case, you could move indefinitely without ever encountering a wall or boundary, even returning to your starting point along perfectly straight paths without encountering any edge. This perspective opens a completely new view of cosmic geometry. If space is closed, it can curve around itself, forming three-dimensional manifolds, loops, and spirals that human intuition struggles to grasp. You could follow a straight path and end up at your starting point, or encounter the same galaxy from different directions, much like a repeating video game. Space becomes a logical map where boundaries, edges, and exteriors exist only in our limited thinking, not in physical reality. Manifold models and closed spaces, from three-dimensional spheres to dodecahedral manifolds, all illustrate that the universe can rotate around itself without borders and without a privileged location. Any point you choose can be considered the center, but only in the sense of your own observation. Even more astonishingly, in every frame of reference, each person experiences a miraculous symmetry. Space is impartial. All points are alike in essence. All directions obey the principles of homogeneity and isotropy. When you look up at the sky, all galaxies drift away, and another person at an infinitely distant location observes the same from the center of their own observable sphere. The universe becomes a continuous network, harmonizing in silent yet powerful ways, where every observer is the center of their own experience, but no one holds absolute dominance. And this, although abstract and beyond intuition, brings comfort. No central throne is needed, no absolute anchor point. Everyone is placed at the center of a sphere of light, with the history of the universe converging into their eyes. Every observation, from the nearest stars to the most distant light, is part of you, part of your personal experience of a vast, boundless universe continually unfolding infinite possibilities. The universe has no borders, yet this does not diminish the uniqueness of each point within it. Instead, it offers us a poetic vision, where every person is the center of the observable universe, reflecting upon the past, the present, and the endless possibilities that the cosmos still keeps hidden. If you pause for a moment and look at the star-filled sky, you might wonder, does the universe really have a boundary? A sudden wall separating the observable from absolute nothingness where no space, time, or physical law applies? The answer, according to modern understanding, is both theoretically plausible and difficult to grasp. A physical boundary, if it existed, would raise countless thorny questions. Would light reflect or stop there? Would matter become distorted, frozen, or disintegrate? And if so, how could such a wall form in a universe that is constantly expanding, constantly drifting? Most modern cosmological theories simplify the issue by eliminating boundaries. No borders, no conditions, just a smooth, continuous space where light and matter move freely. And even if some distant boundary exists, light from that region would likely never reach us. It would lie beyond the cosmic horizon, forever hidden from view, like a ship gradually disappearing over the curve of the Earth. We know of its possibility, but can never confirm it. That thought brings a particular sense of humility. Humans do not control the universe, yet are placed at the center of personal experience. You can smile when someone asks about the edge of the universe because it is like asking what is north of the North Pole. Not a foolish question, but based on an assumption about a structure that does not inherently exist. The universe, it seems, favors curves, loops, and infinity. It does not need corners, enclosing walls, or containers. It stretches and folds subtly, quietly, challenging the intuitions we grew up to trust. Space is only part of the story. When we look at time, our brains like to think of it as a straight line, an arrow extending from past to future. From birth, school, work, to retirement, time seems to flow evenly, neatly, and rationally. But nature rarely follows neat rules. In the deep architecture of the universe, time, like space, is not fixed. It can bend, stretch, and sometimes twist, forming closed curves, time loops, where a moment can return to itself. Einstein, with general relativity, showed that time is not a passive backdrop. Mass and energy warp spacetime, affecting the passage of time. Clocks on mountaintops tick faster than clocks at sea level, and GPS satellites must account precisely for this curvature. Near an extremely massive object like a black hole, time slows dramatically. This is not fiction, but measurable reality. And if gravity can bend time, why not twist it into a loop? Closed time-like curves appear in certain special solutions of Einstein's equations. In theory, one could follow this loop and return to the starting point, not just in space, but also in time. Imagine baking, leaving the kitchen, taking a strange detour, then returning to find yourself still stirring dough or resting. This imagination carries the classic paradox, like the grandfather paradox. If you travel back in time and prevent your grandparents from meeting, would you still exist? To preserve causality, physicists such as Stephen Hawking proposed the chronology protection conjecture, suggesting the universe would prevent any attempt to create time loops through quantum effects or physical instability. However, this does not mean time must always be linear. Time can be flexible, curving around regions of gravity, even forming circles, repeating cycles without necessarily causing paradoxes. Some cosmologists even imagine the universe as a cycle, expanding, contracting, then bouncing back in eternal rhythm. Along with space, time becomes an active character in the story of the cosmos, not a passive backdrop. The flow of time depends on mass, velocity, and the geometry of spacetime. A moment long to you may be a blink to someone near a black hole, or an astronaut near light speed returning to Earth may be younger than those they left behind. The arrow of time, in essence, is not a permanent feature of fundamental physics, but arises from entropy, the tendency of systems to move from order to disorder. Yet, in some curved structures or low entropy environments, that direction is unclear, opening the possibility to imagine time as flexible, winding, and repeating. In that context, the holographic principle emerges as one of the most extraordinary ideas. It states that everything in the three-dimensional universe, including time, can be encoded on a distant two-dimensional surface. You may imagine living in a three-dimensional universe, but the depth, shape, and even your experience of time are projected from a flat boundary far away. Space and time are not just matter and distance, they can be representations of encoded information. Thus, when you close your eyes, try to imagine. Time is not an endless straight line, but a soft ribbon winding around regions of gravity, forming closed loops, cycles, and rhythms of its own. Every experience, the chair you sit on, the cat you stroke, the light from distant galaxies, exists within a universe of intricate structure where space and time continuously intertwine, stretch, and project endless possibilities to us. Perhaps it is a humble perspective, but also a poetic one. You do not merely live in time, you are part of time itself, bending, twisting, and mysterious, like the universe itself. If you can imagine the universe as a three-dimensional photograph, then the holographic principle presents a concept that makes the imagination quiver. All the information describing the three-dimensional world could be stored on a two-dimensional surface. Like an embossed plastic card creating a deep image, every note, every wave of light, and every particle of matter could be an emergence from data encoded at the boundary of the universe. When this idea is extended to the scale of the entire cosmos, a seemingly simple but profoundly challenging question arises. Could all three dimensions that we perceive be merely the tangible result of data encoded on a distant boundary? And if so, the notions of space, time, and matter, foundations we take for granted, become emergent products of a flat, astonishingly subtle canvas. The origin of this idea is closely tied to the deepest mysteries of black holes. These gravitational monsters in the universe, where gravity is so strong that even light cannot escape, once confounded classical physics, matter falling in seemed to vanish forever, evading all observation. But quantum mechanics asserts that information, any information, cannot be naturally erased. In the 1970s, Stephen Hawking discovered that black holes are not completely black, but emit a faint radiation, now called Hawking radiation. As a black hole gradually evaporates, the thorny question arises: what happens to the information about matter that fell into it? Despite the disappearance of matter, the information is not destroyed according to quantum mechanics, but is thought to exist encoded on the event horizon, a two-dimensional surface marking the black hole's boundary. From this, the holographic principle gradually emerged, like a seed sprouting from the long nights of theoretical physics. By the late 1990s, the breakthrough discovery of Juan Maldacena brought a major mathematical advance. In the antecedent space model, the entire universe could be described by a quantum field theory on its two-dimensional boundary. This created a kind of cosmic twin map, where every feature inside could be perfectly mapped from information on the boundary. Space, time, gravity, and even particles are no longer absolute foundations. They emerge from rules encoded at a deeper level. Imagining gravity in this context is like feeling the warmth radiating from a campfire you cannot see. It exists, can be sensed, yet its fundamental nature arises from flat data. Living in a holographic universe does not mean that everything you see is illusory. The chair, the light from galaxies, and even everyday interactions still exist. It is just that the mathematical framework describing them may reside at a different depth or on a hidden flat surface. This idea has its own allure. The universe operates efficiently, like an elegant equation written on a blackboard where stars, dust, and light are only the emergence of patterns inscribed on a distant wall that human eyes have never seen. Beyond three dimensions, string theory opens an even stranger world. It proposes that fundamental particles are not points but vibrating strings, and the type of vibration determines the kind of particle that appears: electron, quark, photon. However, for strings to operate consistently mathematically, they require more than three dimensions. These extra dimensions are not for seeing or walking through, but are compacted extremely small into complex shapes called Calabi-Yau manifolds. Every fold, every twist in these dimensions determines the universe's fundamental properties: mass, forces, even the physical constants we consider fixed. It is like discovering that your personality is shaped not by upbringing or genetics, but by invisible folds in your bedroom ceiling, both astonishing and elegant. These extra spatial dimensions also give rise to the multiverse hypothesis. Different regions of a larger universe may possess their own configuration of hidden dimensions, resulting in entirely different physical laws. Each universe could be its own musical composition, with distinct melodies of matter and interacting forces. We live in one composition, harmonizing with other universes, yet we cannot yet hear the full symphony. Moreover, extra dimensions help explain certain physical mysteries. Gravity, weaker than other fundamental forces, may wander into these dimensions. And although they are too small to observe directly, they leave subtle traces in high-energy particle collisions or in the delicate ripples of gravitational waves that scientists are seeking. In this model, the universe is a masterpiece of information. The three dimensions we see, along with forces, particles, light, and time, are emergent layers from more intricate structures hidden deep within extra dimensions and holographic boundaries. Imagining the universe this way is not meant to complicate, but to allow us to recognize that reality has multiple layers. What we experience, what is computed in mathematics, and what quietly lies behind a veil just out of reach. It is both inspiring and humbling. We live in a magnificent three-dimensional universe, yet its origin, nature, and deep design may reside on a two-dimensional surface or within tiny dimensions that the naked eye cannot see. And perhaps that is the most poetic part of modern physics. Every discovery is not merely an answer, but a reminder that the universe remains vast, intricate, and more mysterious than any imagination. Every particle, every ray of light, every passing moment could be a reflection of a deeper structure, a complex blueprint encoded from distant boundaries or spatial dimensions we have never entered. And in that grandeur, every moment of existence becomes precious. Every dream of the universe becomes a journey into the hidden depths of reality. The universe, as we see it, is an intricate, vast, and ever-changing tapestry. But that tapestry is woven not only from stars, planets, and galaxies, it is also embroidered with light, with gravitational waves, with invisible quantum oscillations that we can only sense indirectly. Each observation, each photon passing through a telescope lens is a piece of this enormous picture. And those pieces continually tell us about a reality not always directly perceptible. Because beyond our observable region, the universe may stretch infinitely, or be rugged, or curl according to laws that mathematics and physics are only beginning to reveal. Its true shape could be a complex network of curved space-times, where each point of light, each galactic peak, is a note in the cosmic symphony, resonating from hidden spatial dimensions that we have never seen. The expansion of the universe adds another layer of mystery. When the Big Bang unleashed the first moments, the universe underwent a rapid inflation, faster than the speed of light, stretching tiny quantum fluctuations into the seeds of galaxies. In that instant, space shaped itself, not by will, but according to inherent natural and silent laws. Like a river flowing over rocks, forming waterfalls, canyons, and plains, the expansion created voids and galactic clouds, a picture we can observe and study. But most of the universe remains out of reach. It stretches too far, and light from there has never reached us and may never do so. It is a limit both terrifying and sacred, reminding us that we are observers, not owners of infinity. Each of our observations is a silent dialogue with the universe. When light from distant galaxies traverses billions of years of space, it carries messages from the past, recording traces of events that occurred when the universe was still very young. These photons are like ancient letters sent across vast unknown distances, yet still finding their way to converge into our eyes. Through telescopes, we listen to those whispers, note by note, and construct the shape of the universe from indirect data, galaxy distributions, redshifts, large-scale structure, cosmic background radiation. Each observation is a step forward, each measurement a brushstroke on the panoramic picture we have never seen in full. Yet there is a wonder in these very limits. When we realize that most of the universe has not yet unfolded before our eyes, we learn to cherish observation and reason from what can be known. Even with countless modern telescopes, from Hubble and James Webb to radio observatories, we must rely on models and assumptions about the homogeneity and isotropy of the universe to transform local observational fragments into a comprehensive picture. This is a profound lesson in how we approach reality, not through control or possession, but through observation, listening, and grounded imagination. Hidden spatial dimensions, the subtle folds of space-time, might also contribute to our understanding of the universe. If the universe has extremely small extra dimensions, curled like delicate petals, then every force and fundamental particle we see emerges from that structure. Space is not merely empty, it is an instrument, where the quantum notes of particles and light vibrate according to concealed dimensions. Thus, the reality we experience is a complex synthesis, where each observation reflects the underlying hidden geometry. The interplay between the shape of the universe and observable light also raises profound philosophical questions. If we cannot see most of the universe, we can still understand it through the signals, interactions, and laws that light conveys. Human knowledge is therefore not limited by infinity, but shaped by our ability to receive and interpret the signals the universe sends. This is a quiet yet deeply reverent perspective. Space is not to be conquered, but to be listened to learn how to understand its structure and laws. The shape of the universe, from the observable bubble to hidden spatial dimensions, also mirrors humanity in our cognition. The brain, with its folds, mirrors curled dimensions. Twists, wrinkles, and tangents of memory and imagination create the patterns of reality we perceive. Every observation of the universe, every measurement of light from the past, indirectly projects onto the structure of our own mind. Thus, exploring the universe becomes an inward journey where humans and space connect in a harmonious, silent, and eternal rhythm. And then, when we look up at the night sky, the stars are not just points of light, but reminders of scale and the mystery of everything. Their light, cosmic ripples, and the delicate structures we observe are notes in an endless symphony. They invite us to reflect, to learn to listen rather than conquer, to realize that shape, expansion, hidden dimensions, and light are all components of the same story, the story of reality, of ourselves, and of the capacity to understand beyond sensory limits. The universe, in all its vastness and infinity, does not need to be complete within our sight to be whole. Even the small observational fragments we possess, when combined with imagination, theory, and mathematics, are enough to reveal its shape, rhythm, and intricate structure. And it is precisely this silence, this subtle harmony between observational limits and intellect that creates the profound and sacred beauty of studying the universe, a beauty guided by light, defined by shape, and eternally sought by our minds. Perhaps the greatest wonder is realizing that we do not merely exist in the universe, but that we ourselves are a part of its geometry. Every thought, every heartbeat, every breath is a local oscillation within the endless flow we call space-time. You are not standing outside to observe. You are integrated, a dancing element within the vast structure. Your nuclei were once born in the hearts of stars, and from there, they continue to carry the story of light, of gravity, of expansion. When you feel your heartbeat, you are listening to a rhythm that has echoed from billions of years ago, a rhythm the universe set for all living beings to follow and harmonize with. And if you wonder about shapes that science has not yet confirmed, such as Calabi-Yau manifolds, Taurian dimensions, or holographic screens, imagine them as doors leading to unexplored mysteries. Not to possess, but to contemplate, to realize that the act of questioning itself is a profound experience. Those mathematical models, even if they exist only on paper, open a landscape where imagination and reality intersect, where we learn to perceive the universe not only with our eyes, but with sensation, intuition, and understanding gradually absorbed over time. The stillness we feel is not meaningless emptiness, but a subtle order, where every element, from distant galaxies to the fundamental particles in your body, coexists according to a delicate law. It is like snow falling in a forest, silent yet not chaotic, gentle yet structured, and it is within that silence that we find a special peace. There is no need to decode every curve or every fold of the universe. It is enough to know that you are a part, that the question exists, and that immersing yourself in the flow of awareness is itself a form of exploration. The shape of the universe in light and darkness, in folds and endless voids, is a melody resonating, and we can listen to it. Not to possess or fully comprehend, but to feel the rhythm, to immerse ourselves in the continuity and infinity of reality. When your eyes close, when your mind relaxes, you can sense each oscillation of time, each wave of light, and each faint fold of space-time. Each such experience is a moment of contact with infinite vastness, a reminder that although we cannot grasp everything, we can still touch some part of it through sensation and contemplation. And that is the greatest gift the universe offers. Not a final answer, but the ability to rest in questions, to find peace within structured stillness, to listen to a melody that can only be truly heard in silence. Amid the vast emptiness, among distant stars and spreading light, you are a note, a heartbeat, a breath, and in doing so, you are the living, dreaming, feeling universe, even in the silent night.